Let me tell you the background to the talk very briefly, which is that when the idea of the symposium came up, I gave Bengt several titles, and he chose one, which was Origin of Life. And then we discussed this a bit and changed it to water. And now that I see exactly what the audience is, we're going to talk about robots. So there is a rationality to this, but it's not obvious. And if you want to know what the greatest requirement is for a modern scientist, it's flexibility. Okay, so I'm going to talk about soft robots. And the questions are, what are they? You know, what is a soft robot? And an important question in all of science and technology is, who cares what they are? I mean, it's always a good thing to know about. And then, particularly for those of you who are beginning your careers, I want to talk about robots generally, because this is a big subject. And I'm not going to talk about that because that's a subject for old men in a moment. So, what is this? This is gold coins. And there was a period when, if you thought about how nations competed with one another, what they did was compete for gold, oil, land, soldiers, things like this. And the world that those of you who are students grew up in is sort of the residuum of that world. Stuff was what people competed for. Now what they compete for is basically you, by which I mean what the major object of wealth, power, whatever you like, running the world is educated people able to do complicated jobs. Now, this particular problem is often faced or phrased in terms of simplification, so that we've heard for years, everyone in the room has heard for years about the competition between Europe, the United States, and let's say China, phrased in terms of expensive labor versus inexpensive labor. That's gone away now. The Chinese are getting to be as expensive as we are, and we're getting to be as cheap as the Chinese are, and the quality of the workforce is turning out to be about the same now, and very soon much of the world will have, much of the developed world, including China and India, will have the same ability to compete with you as you do have the ability to compete with us in the US or elsewhere. So that isn't going to be probably so much a thing in the future. What's more interesting, I think, and more significant for you and actually for us as a species is this question of not humans competing with humans, but humans competing with machines, or humans competing in cooperation with machines. So the issue is not human versus human, it's certainly not oil versus gold, it's more human, machine, are we going to work with the machine, are we going to work without the machine? So the new element that I want to inject into your life, and which I think is the transforming element actually for the next period of time, is actually robots. So, the world population will peak at about 12 billion people. You would think it would go on forever, but what happens is that as educational levels go up, women get less and less interested in producing large numbers of kids. You don't need to have as many kids to have insurance policies. So everybody seems to agree that this number will be about right. But there's an interesting problem which comes up, which is that historically there has been in the developed world a middle class, very rich and small number of very rich, a small number of very poor, and then a lot of people who have good jobs, by which I mean secretaries and dental assistants and clerks and computer programmers and whatever. The trouble is that that middle class is often now being replaced by machines. Not necessarily robots, but by machines. So the middle class, the complex, interesting jobs are disappearing, and there are more poor jobs and more of the wealthy. And these divided societies are not terrific societies. They turn out not to be very stable. So we need to think about what that's going to look like. And let me just give you a few examples of robots, pictures, and I'm going to show you movies soon. I want you to know that I'm on your side. I really shouldn't be up here talking. We all know that all education comes from YouTube. So I'm just going to be a video transmitter to you. This is an assembly line, and these devices here are robots. And the thing that I'll tell you is you cannot get anywhere near that line because when one of those arms swings, it doesn't even know you're there. And so it just goes right through. To give you a Tony word to use in your party conversations, the word is cooperative and non-cooperative. These are very non-cooperative machines, meaning they cannot work anywhere near people. This is a kind of drone, a kind of robot that's being highly developed and represents something which happens in the world, which is a lot of investment by the military in advanced machines. This is an extraordinarily stupid machine. That's something called a Roomba, which is one of the world's most inefficient ways of sweeping the floor. This is the Da Vinci surgical robot, which doesn't actually make surgery works better, but makes it a lot more profitable. And this is Mars, and here are some devices which I'll show you in a bit. Now let me give you an example of a non-cooperative robot. And we will see here if the video works, and if the sound works. Sort of. There we go. The question is, do you want to hire that as a babysitter? But look at this. This is really stunning. Look at the grace with which this balances, shifts its weight, compensates for a change in mass, compensates for momentum. And what you should know about that is that there's no brain. That's all accelerometers and local feedback loops and things of this kind. So this is done by a company called Boston Dynamics, which is an extremely interesting company which focuses on non-cooperative robots. Now I want you to consider a world in which you take that kind of thing, which I can't tell just with my not very good eyes, I can't tell whether it's alive or not. It's so graceful in its physical movement. And I combine it with artificial intelligence. Will we be able to understand whether we have something that's alive or not alive in the future? How are you going to tell? And there's a test that you should all know about, which is called the Turing test. It comes in several versions, and this is the simplest of these versions. Mr. Turing, for those of you who haven't seen the movie called The Imitation Game, it's a terrific movie. Turing was an early computer scientist who had great influence in World War II. But Mr. Turing proposed the following idea, that if you have developed something which is a machine that might think, that might be intelligent, how do you tell whether it's a machine or one of us? And his idea was you put up a screen and you're on one side and the machine or the person or whatever it is on the other, and you talk with one another by computer. And if you can't tell whether you're talking to a person or a machine, that's the best you can ever do. So there is no absolute test, it's an operational test. Intelligence is what it seems to be. So you can't actually tell whether I'm alive or not. And I, just to be symmetrical about it, can't tell whether you are. We might all be papier-mâché. And that raises some really interesting questions about a world in which the ability of machines to do what we can do can't be distinguished from things that are now alive. So we have been interested in this problem from the point of view of looking at cooperative machines. That is, we want to make things that have the characteristic that they do operate smoothly with us. And the origin of this project was here. And you say, good heavens, what's there? That's a Coca-Cola can. But the original project that we had was to build a device that had the characteristic that it started out looking like a Coca-Cola can. On request, it would unfold into something flat. The thing that was flat would undulate across the floor, find a door, crawl under it, and then reconstitute itself on the other side as something that looked like a Coca-Cola can. You can see why there might be people who would be interested in that particular task. I'm not interested in that particular task, but I am interested in the general problems that it poses. So here's our starting point, and amazingly enough, we certainly don't have that, but we have some things that are surprisingly like that. But every program, I think, should have a totem. What's a totem? A totem in English is an animal that represents what you think to be the essential features of the problem or the person. My personal totem is a rhinoceros because they are so stupid and so nearsighted that they try to solve every problem by going through it. And this is the substitution of forward motion and momentum for intelligence. So this is the totem for this problem, and I'll show you why it's such an interesting and really stunning animal here. What I want you to do is to watch what it does that we cannot do and that a hard robot cannot do. So look at the sinuous grace by which it manipulates its tentacles. And I'm going to run the whole program because there's just a bit at the end that I'm particularly fond of. The octopus brain is quite plastic. I think it's squeezing through at this point. Of course, it doesn't have any bones, so it's soft, and hence its relationship to our program in soft robotics. Here it's pulling through the aft part of the octopus. I don't actually know what part of the octopus that is that's coming through, but I want you to look at this look of intense satisfaction on its face. So this is where we started, and the characteristic of this is that it's about as simple a problem as you can find. That is an uncooked egg. If you try to pick up an uncooked egg with a conventional robot, it turns out to be a really hard problem because you have to have pressure sensors, you have to not pick up with too great pressure because you'll crush the shell, things like this. What this is basically just a balloon. So you have here an elastomer. It has the structure in which there's a layer that's flexible but cannot stretch, another layer that's flexible but can blow up when you inflate it with this little pneumatic line here. And when it blows up, this part expands, that part simply bends, and it reaches around the egg. And it can't apply more pressure than the pressure that you apply on the input line. So it's automatically self-regulating. And it does something that you can't do with a hard robot. Now, there's something I want you to look at here, but the major thing to look at is this. What you see is one of these tentacles that's blown up, and what it looks like is a series of little balloons, if you look at this. And I'm going to show you how you make such a thing in just a moment. You can make them very easily. I also want you to see something else, which is that as these tentacles curl, they curl from the tip. That turns out to be what we call in science a materials nonlinearity. And it is an extremely interesting, underexplored, and useful part of this particular world and problem. How do we make these things? Very entirely straightforward. You use a 3D printer, which I suspect all of you are familiar with from MakerBots. You make molds. In the molds, you pour a polymer that is a soft elastomer. And to give you an idea of how soft is soft, these are the same polymers that are used for cheek implants and breast implants and things of that sort. So it's that general texture. And then you paste these together in some appropriate way, and you can go from a design to a device in the course of a morning for nothing. And it turns out that high school students everywhere are now making these things. And this is pure envy, Ahmed, wherever you are. I refuse to be seconded in important things like musical interludes. So the reason for showing this is that one of the questions that people asked at the beginning is, can you make these things operate rapidly? And although I'm not going to show it, you can actually make a chameleon tongue which can catch a fly. It catches a fly one time out of 100, but that's because there's no chameleon backing it up. Now, what about the undulation part? Well, here is a walker which is undulating, and there's a kind of clumsy walk, and here it gets to the barrier. That's a glass plate, and you say this really doesn't look to you like a fantastically flexible and agile object, and the reason for that is that this does have a sort of brain, but the brain happens to be a Scottish postdoc who's off screen, who's running a series of of chambers. This has 5 chambers. There's one here, and then one here, here, here for each leg. So it involves 5 switches, and this is complicated in a country that, I won't say it. It just has something to do with sheep. But so what you'll see, and I again want to go all the way through, it's almost heart-rending, the ends of this. It manages to ooch its way into this. We have technical words for these gates like ooch and walk. And so here it is, and it's trying so hard. And then at this point, it almost gives up. Blah. And then it will reconstitute itself, gather its strength, and go on and walk off on that gate. But so, we have something that goes under the barrier now. But I want to show you a contrast. Here is another one of these nice devices from and I want to show you this to make a case. This is a device called Wildcat. And it's run by something that's effectively a lawnmower engine. And it's actually a very clever device. And it'll go off here and prance its way back. And there are a couple of things to know about it while you're watching it. One is that this is, roughly the size of a pony. A pony operates on about half a horsepower because it's about half the size of a horse. This operates on about 50 horsepower. So it's about 100 times less efficient than an animal is. And we don't actually fully understand why there's that difference. And that's an interesting problem in basic science, connecting physiology and mechanics and molecular science to think about. And it's a good runner, gallops along, but there is a little something, yes. I just wanted you to know that they may not be infallible, these devices. This is another reason for not getting too close. Now, we can do the same thing, but we just do it more slowly. And here's an example of something which is untethered. It's got this is the device. It's got a little compressor on the back here and a Bluetooth link, and it is clearly much better than the device I showed you if what you have in mind is the object for your morning's recreation is to crawl under a laboratory bench and look at a TV set that happens to be under there. Probably not what most of you do, but it operates that way. All right, now let me show you another thing which is interesting about these systems. And this first thing that you've seen in a slightly different fashion, this is now a hand-shaped object picking up an egg. This has the equivalent of knuckles built into it, and one of the things that you can do with this is to explore what we call in the group life that never was. So we can make hands that have 7 fingers and hands that have 4 thumbs and hands that have claws and hands that have all kinds of things. They're very easy to make, and this picks up, and that's fine. But what I really want to show you is the next thing, which is this, that's a hammer. And this, ouch. And to show you that it's real, there. Now, the point of that is that you almost can't break these things. I mean, for example, we've done the experiment of throwing them off skyscrapers, and the terminal velocity, because they're lightweight, is not enough to do them any harm when they hit. You can cut them, but you can't break them by blunt impact. You can shoot a bullet through them, but you can't do otherwise. It means they're almost indestructible, and you can't do that with a hard robot. And there are a bunch of other things that you can do, and I'll just show you one, for example. Suppose that you receive in the mail a polystyrene box, and you're really not sure what's on the inside of it. This particular combination of things, well, you take something of this sort that has a needle, it drips acetone on to dissolve the casing. Here's the dripper. This part, corresponding tentacle, has a little camera in it so that you can look at what's there. You can, if you take acid and drip it on any contacts that you might find in there. It is, it's the potential to be useful for people who do, for example, counterterrorism. But there also are some very interesting ideas that are much simpler, and this is an example of rehabilitation. When you're a little older, one of the things that you run the risk of having happen to you is a stroke. And after a stroke, depending upon where it is, you may find that part of your anatomy isn't working. And it's very important that someone manipulate your hand, let's say, to avoid the development of spasticity, which is basically the permanent locking of fingers or something into position. So that's not a particularly interesting job. What we've done here is simply to take these finger-like objects and strap them on a glove from a hardware store. And when you do that, then you can do the flexing. So here's a case where the machine is designed to be compatible with people. I mean, compatibility is the key. And you can also do the same use the same kind of machine to strengthen a grip if your grip is weak for some reason, or to give you extra control if you have some problems with neuromuscular control. These will be, it's clear, very simple and very interesting systems to work with. Now, just one small thing in terms of science in this. This business of working from the end, opening and curling up like that, is actually a very subtle and very interesting scientific material science problem in nonlinearities. And one reason why it's interesting is that it opens the door to one of the features of these systems that I'm particularly attracted by, which is that if I wanted to build a hard robot that did that, I'd have to have a whole bunch of servo motors and sensors and things like that to start curling up from the end. I don't have to do that here. And so what these offer is the opportunity to replace control systems with the properties of materials and designs. And that gives a lot of room to simplify the system. Now, two final examples. We're not fixated on squid. We don't have a particular thing for squid. We also like spiders. And I won't go through the details, but spiders' joints are extremely interesting. I mean, it's a very clever piece of design. And so you can begin to use other animal models. And this particular object is designed with 6 legs like an ant, but it operates with the same joint actuation mechanism as a spider. And I won't go through the details, just everywhere that you look in the animal kingdom, there are different designs of actuators, and all of these can be thought about in this fashion. I don't actually know what this video is. Oh, yes. This is the water strider. And so here's another one of these kinds of things. And what you see here is a device that's light enough in weight and can be tinkered with in terms of surface properties so that it sits on the surface of the water. You can't do that with a heavy conventional robot. All right, let me begin to close up with 2 things. One is the summary. The first is, soft robots should not do things other robots can do, hard robots. It should work. These are designed to work with people and to be cooperative. Collaboration is the key. Robots are going to happen, but I think it would be awfully nice if the scientific and technical community built robots that improved or augmented the capabilities of you rather than competed with you. Cost is a major advantage. These are inexpensive enough they can be used once and thrown away. And then applications, there is just an enormous number of things you can do with these. So surgery, because they're soft, rehabilitation prostheses, I've talked about this. Handling fruit, I'll show you an example. Search and rescue, as in Fukushima, where you want to send something in to take a look and then throw it away. Hazardous tasks like mining. And then gripping. And it turns out that the big deal in terms of applications is actually gripping. And this is from a company that's spun out in this. The first paper in this was published in 2011. In 2013, we started the company. And this is what the company is doing. And there are a number of things here that are illustrative. These are all grippers. This answers the question of, can it pick up heavy weights? This answers the critical question of, can it pick up potato chips? And that turns out to be very hard, because if you pick them up wrong, they crack them. This is fruit picking. Look at the dexterity of that. These are very fragile, lightweight things. Gets picked up. And then a task which we all face almost every morning of picking up cacti. Now, there are a couple of other things very quickly to show on the same video. Look at the versatility and the agility of this system. This is our gripper here coupled to a commercial arm. And the characteristics of that, look at this is really neat. Catches it. And we'll put it down. These will be used almost certainly with a combination of a mechanical arm and then something of that sort to put things on the top. So what the point in this, oh, and yeah, that part was actually very interesting. I don't think I can go back and do it again, but the point is that on these combinations of mechanical arms plus effectors at the end, you want to be able to change from one to another, and this is just a question of picking one off and clicking the other one in. So this is a case where one can go from polymer science to robotic technology to commercial application in just a couple of years. And I want to close with this last point here. The names of the people here are not so important since I think you probably don't know most of them. But what I would like you to look at is the combination of national backgrounds and areas. So US in material science and chemistry, Spanish in electrical engineering, Singapore chemistry, Italian nanoscience, Chinese applied mathematician, German applied physics, Canadian robotics, Iranian bioengineering, US material science, a couple of Turks in chemie and material science, Chinese and Canadian in mechanics and bioengineering. The point in that is that it makes the case that the workplace in which you will work is truly international. With all of that, the strength of that, you'll be working with people from everywhere who know all kinds of stuff, some of them better than you do, and in which there's the advantage of that, but also the competition. And I'll just mention one person here. Where are we? Here. Dian Yang is a good example. Dian came from a little town in western China. He went to Beijing as a mathematician, thought that was pretty easy, and went then to William and Mary, which is a liberal arts college in the United States, for a year or two to learn English and figure out what Americans did. Then he went to PhysTech in Moscow, which is their equivalent of Caltech to do mathematical physics. Came back to the US and went to Harvard to learn theoretical fracture mechanics, thought that was too easy, and then came to work with us because he thinks that experiments are really hard. But this is what you're going to be working with in the future. And it really should stimulate your enthusiasm for cooperation and also just a little bit sharpen the teeth because there's some really smart people out there. And I think that's it, and I thank you very much. And it's not what you expected to get.
We have time for 2 questions.
I heard about you talking about artificial intelligence overall, and as we all know, robot technology overall is improving a lot in the past years. And isn't it becoming humans are becoming a bit obsolete in the future when robot technology and AI are improving this rate? How long is this going to be? And
that is the question. Yeah. I mean, the issue in this, which has, I think, people who are, why do I say it's a big deal? The big deal comes from the fact that the combination of machines and artificial intelligence holds up a possibility which we cannot evaluate that we may be able to create a peer competitor. That is something which is perhaps intelligence. We don't know whether intelligence uniquely requires a brain or whether it can just require something else. A robotic intelligence would probably not be us, but it would, on the other hand, have access to the entire Internet of Things all at once, so it would be a distributed intelligence. There could be pluses or minuses, but I think the basic question of is something that computes, if it computes in a complicated enough way, is it automatically some form of intelligent or self-aware? We don't know the answer to that. So it is exactly the right question.
Another young man. Microphone.
Ahmed.
Wait.
Oh. When you mentioned the nonlinear behavior, did you mean actually nonlinear in the displacement that we have or in the feedback mechanism that exists?
What you're seeing there is a behavior that's called, in the materials world, snap-through. And you see it in a balloon. When you take a balloon and you start blowing, it's very hard to get the first part to expand, but as soon as the first part is expanded, then you get expansion of the rest of the balloon. And this is a case where the stress-strain curve is reentrant in a sense. So I'd have to draw you a picture, but what it is something in which you increase the stress, the pressure, the volume goes up, and then it jumps to a different state, and then when you deflate, it follows a different pathway down, and then it jumps to a different state. That's a nonlinearity in this combination. And by the way, it may be what's going on with climate. That is, jumps, not continuous movement from one to another, but jumps from different states. So there's a lot to be learned from materials and chemistry that applies in other areas if you think broadly about science.
One more question from a real youth.
Hi. Well, I have two questions, but it's in
Where
one.
are you? Oh, there you
Sorry.
are.
Wait, can I ask now?
The
Okay,
guy
I'm
with
sorry,
the
I'm
long
not
hair.
sure. Whichever.
Oh.
I like disembodied intelligence. I think this is a great idea.
Here I am. Well, I would ask, like, is it possible to manipulate the thickness of the balloons in a way that you can, so they don't just turn at the end, but maybe at specific points? And also, if you can apply, like, sensors to the ends of them so they can work as feelers for, like, chemical or radiation or light or...
You asked two questions. One is the question of can you vary the thickness or can you vary the tensile strength or something like that. Exactly, again, the right question, because what that gives you is another easy to manipulate design parameter which can lead to interesting properties. So we are pursuing exactly that. The sensor issue is a little bit more complicated because one of my philosophical beliefs is that you want to make things as cheap and simple as possible. Ahmed and I fall exactly in the opposite ends of the spectrum. He wants to make them as expensive and complicated as possible. I want to make them as cheap as possible. Yeah. So you're getting the alpha and the omega of the intelligence spectrum with alpha over here and omega following up at the end. But the thing is that if you make it simple enough, then other people will start using it. Yeah. And we've always had the point of view that if you're doing science and technology and other people are not using that science and technology, then you're not going anywhere. So keep it simple. But just, one point of calibration in this, we use to blow these things up about half an atmosphere, which doesn't sound like very much, but it turns out that's the difference in pressure between the top surface and the bottom surface of the wing of a 747. So half an atmosphere per wing will lift about 1 million pounds. And so you've got lots of room to move around in this. But a very good question.
So we take a break now, but first we thank George once more.